Okay, yeah. So, as I said, my name is Natasha, and I'm a PhD student here at Birkbeck, but I spend most of my time at the Natural History Museum because that's where the meteorites are, and that's where the instrument is. And it's closer to my house, so that's kind of useful. So, I am kind of going to give you an introduction to the technique and also talk about a few ways that I've been using it within my PhD. It is, unlike the other talks, mostly unfinished work. So, what I'm going to talk about first of all is why meteorites are interesting in the first place, the things they can tell us, why we want to use computed tomography as a technique, how it works, what it is, and then a couple of examples of the first exploratory kind of stuff we did, because we really weren't sure, so we kind of stuck everything in it. That's the great thing about non-destructive techniques. And then look at, in more detail, about some case studies where I've been trying to dig a little bit deeper, using the method not just for imaging, but also for some kind of quantitative analysis. And hopefully the videos will work. So, why meteorites? The others have touched on this quite a lot. The solar system is a really interesting place. And depending on what type of meteorite it is, it will give you different kind of information. Okay. So, for example, you have your chondritic meteorites, which are a mixture of your metal material, your silicate minerals, pore spaces in between it, and they contain these lovely chondrules forming in free space. This material hasn't really changed, so this is prior to the differentiation that Hilary mentioned, and so this stuff can tell you about early solar system processes and conditions. Then you can move on to the melted meteorites, or the achondrites, and this contains the more familiar sort of iron meteorites, which are representing the core, and obviously we can't study our core, so that's kind of handy. These palisite meteorites, which are beautiful iron-nickel matrix with olivine crystals in, that we think come from the core mantle boundary of these long since smashed up planetesimals. And also, as Louise and Pete mentioned, you know, we get stuff from crusts in the form of lunar or Martian meteorites, and they're fantastic for discussing planetary evolution. So I don't think it's a challenge to say how great meteorites are. And also another reason why we're doing this is a Natural History Museum, which I'm guessing most of you have been to, and it's one of the, well, it is the oldest collection of meteorites in the world. Started in 1802, and it's incredibly important. We've got about 5,000 registered meteorites and an active group, including people who are at Birkbeck. So Hilary is a scientific associate. We've got Nat Keeter at the back, a postdoc shared between the two institutions. And there's a really collaborative space, but it's also responsible for providing specimens to the wider scientific community. We do loans all across the world, and so working on a non-destructive technique like CT is really important. We can be checking that we're looking for the features that people are interested in the samples that they want, so that there's less wastage. And this is, I guess, just a side to highlight that. Basically, all the ways that meteoriticists normally study rocks is destructive, just because of the very nature you have to sample them. So we've got something like up here, which is the Allende CV, and that's just a slab that someone's cut through. We make thin sections of these rocks, so these 30 micron thick pieces mounted on slides, so that we can do things like this one here or this one here, which are similar to Louise mentioned, where you have element maps from EDX, scanning electron microscopy work. So we're either cutting them and slicing them to provide nice surfaces, or for example here, we're crushing them to a powder for X-ray diffraction. That's quite destructive. Or some people fully digest a sample in order to look at isotopes, and that's, you know, even more of a curator's nightmare. So this technique, microcomputed tomography, has been around since about the 50s. You'll be familiar with it in a medical sort of way, but being used in meteoritics is a lot more recent. And so basically it's similar to getting an X-ray at a hospital, except that we use about 50 times the energy because it's much harder to penetrate metal and rock than it is flesh and bone. And we'll scan it for a lot longer. So we are able to have three-dimensional data. You put a sample, so you have a cone beam of X-rays that comes from a source, and then you put your specimen on a stage, and it is slowly rotated 360 degrees completely during one scan, during which there are projections which are collected by this detector panel on the side here. So there's about 3,000 projections, depending on the settings that you want to use. The data that you come out with in the end is grayscale data, and it's an entire volume that can then be viewed in slices in any which way that you want to be. But the most important thing is that the grayscale number refers directly to the attenuation of the X-rays in the sample. That's a function of the energy of the incident X-ray, which you will know from the scanner, but also the atomic number of whatever you're going through. So the easiest way to think about it is a bit of a density map. So the very heavy, dense things are going to appear brighter. It's not always that easy in geology, because you probably know we have solid solution of minerals, there's lots of overlapping densities, so it doesn't exactly give you a fingerprint of what minerals you've got inside, but it's a good place to start. So when you're doing the actual scanning, it's a little bit of an art sack approach. The most important thing in a scan is that it stays still, because any kind of motion while this thing is rotating would cause blurriness in your data. So we tend to sort of, stick test tubes together, and we fill them with oasis or florist foam to try hold it still. And so this is an image of what it looks like within the chamber. So you have the sample, which is on this rotating stage. So this is just to make it a bit higher. It's a big chunk of meteorite in a plastic bag. That's all the preparation you have to do. Stick it in oasis, not too fiddly. And this is what's called the gun. So basically the cone beam of X-rays is coming out of here. There's obviously shielding on the outside. And we put filtering in there as well to sort of get rid of low energy X-rays, which cause artifacts in data and whatnot. So I've said a lot about why it's great. It being non-disruptive is the most important thing, but there's little or no sample preparation, so wrapping it up in parafilm or just sticking it in a plastic bag. The data is pretty quick, so your average scan takes about half an hour. You can do more projections or longer scans if you need to get closer data, or if you have particularly high density. And it's repeatable, so if anything goes wrong, you didn't get the data that you wanted, you can retry it with different parameters, or anyone else can try it as well, which is important. The downsides are this data volume, obviously, it's telling you where everything that's 5 microns in a sample like this is, and what its attenuation is. So the data volumes that you end up with are about 20 to 30 gigabytes each scan. So that's kind of a lot of effort to manage and to back up. It also means that you need high quality computers with a lot of RAM and good graphics cards to deal with it, so it's an expensive technique in that case. The resolution is limited to the sample size, so basically how close you can get the whole sample to that gun will determine how good a resolution you can get. R1, which is a sort of off-the-shelf scanner, can go down to 5 microns per voxel, which is basically a 3D pixel. There are better ones, and people can use synchrotron CT as well, which goes down to much smaller nanometers. Sometimes you get artifacts in the data, especially where you have really high density stuff meeting low density stuff. It's not very happy on those edges, but we can use filtering and things like that to try and mitigate against it. It's just something you have to bear in mind when you're looking at the data. And the sample size you can go up to is limited by the energy of the X-rays. So whatever the maximum X-ray energy of your scanner is. If you're, we've done a dodo before, we can do big things, but when it comes to meteorites and there's a lot of metal in them, we can only really do things that are probably about 10 to 15 centimetres maximum in size. The other thing is that, as I said, it's not been used much in meteoritics. There's not a lot of quantitative data analysis done, so there's not kind of accepted ways of doing this. So hopefully it will be developed in the future. So what I'm going to do is just go through various examples of it, and this is a great opportunity to put Caroline up on the screen. So Tissint was a meteorite, a Martian meteorite that fell in 2011 in Morocco, and it was seen to fall. There's only been 5 meteorites seen to fall, and meteoritists love them because they haven't been sitting on the Earth's surface for very long, so they haven't been sort of contaminated or weathered. So this one, luckily, a really kind person donated a big 1.1 kilogram chunk of it to the museum, which you can go and see in the vault gallery. And so this was when the technique was really new at the museum, so we stuck a few bits in there to see what would happen. This is an example of just a single slice through the CT data. So you can see the different mineral types in here. But then what's most interesting is that we could see quite a lot of these cracks, veins in there. Now Tissint is well known now for having these glassy veins which are indicative of high shock, but they also have entrained weathering products within that glass. And so when we scanned it and saw this bit here, we were pretty intrigued. So I'm hoping that this is going to work. Yeah? Okay. So this is just a video where we are artificially cutting through the CT data, and you can see the big glassy vein there. I have just coloured in where rock meets air as pink, just so that it stands out quite nicely. And so you can see a lot of these veins in here, and the odd few little pockets inside, void spaces. Now, Tissint formed from a basaltic magma about 600 million years ago, And if you zoom in on this bit here, you see there's sort of a cluster of little voids, and there are some cracks that extend from it as well. Now what we could do with the CT data is follow those cracks. Do they extend and reach the surface of the meteorite? And they don't. So we can be fairly sure that there hasn't been any contamination of Earth's atmosphere into those void spaces, which would indicate to us that it actually preserves bits of Martian atmosphere from when the sample was ejected. So the big impact that knocked it off, which they've done this cosmic ray exposure ages to figure out how long it was in space for, and so they think it was ejected about 700,000 years ago, which is really cool. And an exciting thing would be to think, I suppose, when we're talking about meteorites on other planets, would be to think that there are potentially pieces of the Earth on the Moon or on Mars which could, keep a record of early Earth atmosphere. So this is another example which I really like. This is one of the Apollo 16 rocks. And so this is what it looks like in hand specimen. It's mostly that anorthositic stuff that Louise has already explained to you, thankfully. So this is one of the slices through the sample. So the background to it is that NASA didn't have their own CT scanner, and so the Apollo curator brought a bunch of samples over to the museum, and we thought we'll explore what we could find out from them. And on the surface of this sample, you can see that there's a tiny bit of basalt that's exposed on quite a big sample. They call it Big Bertha, this one actually. And he wanted to know how much basalt is there, because from a curatorial point of view, you can see there's something interesting, but you want to know how much have I got, how much could we send out. So we did a CT scan, and actually even just from the CT, we were able to compare the sort of textures to what comes from a thin section of another piece of 60639. So I wonder if this is going to work. If not, we can just play it here. So this is the cool thing about CT really, is that you can just play around with videos and colours. So you can see, I should point to it, there is the piece of basalt that is exposed. And then you can just say, right, remove all that anorthosite. I don't want to see it. I just want to see where the basalt is. So you can see this big basalt cast in here. All these little grains here are probably ilmenite or just really heavy dense stuff in the anorthosite. We also found some other what looked like basaltic cast in that sample as well. But the most exciting bit really, I suppose, I'm just going to minimise that one and go back here, is that we could then say to NASA, okay, this is the shape of your clast, this is the volume of your clast. Based on the mineralogy that we think of this is the mass that you've got. This is exactly where you need to cut it to expose it, and then this is how much material you can send out to scientists, which obviously when you're dealing with a really limited collection set is a helpful thing to have, and they've decided to get their own one now, so lucky them. So this is sort of moving on to more of what my PhD is drilling down into. It started off quite exploratory, and so this is a really nice story. It's Barwell meteorite, which fell on Christmas Eve in the village of Barwell in Leicestershire, and it was seen by carolers and all sorts. And it's an ordinary chondrite, so it's similar to 85% of other meteorites that we have in our collection, and people didn't think it was that remarkable, other than it was the biggest one seen to fall in the UK and, got lots of attention. It wasn't really studied until the 1980s when Bob Hutchison, who was a scientist at the museum, cut it open, and perfectly by chance he exposed this thing here, which has become known as the Barwell pebble. This, unlike the rest of the meteorite, has an igneous texture. It's got oxygen isotopes that are similar to a different type of chondrite, so we split them into heavy, like high metal, low metal classes, and also it had this older age, and so it was, this is the first evidence, or some of the first evidence for this idea that there's a whole generation of early differentiated planetesimals, some of the lost bodies that Hillary's been talking about. So these are just some pictures from the archives, which I really like. Some of the scientists going out there with a magnetic rake, and there's stories of, school kids going and picking bits up and trading them, and it got in the news. This was a nice story of a policeman and an inspector called out to a house because elderly couple actually reported ruffians throwing rocks through their window, and all sorts of bits like that. And apparently they're still finding pieces. One guy tried to sue the church for, it hit his car, and the insurance company said, oh no, you know, that was an act of God, we won't reimburse you for the damage to your car, and so he went to the church and said, like, oh, you better pay me back then. I don't think he got anywhere with it, but anyway, it's nice stories of meteorites in the UK. So what we did with the sample was stick it in the CT scanner, see what would happen. And so when you look at a screen like this, basically that is a 3D representation of it. And then here is like the XY plane, the XZ plane, and the YZ plane. So you can basically cut it in 3 different ways. You can cut it any way you like, just by rotating it, but this is easy enough. And so I saw the original pebble, which is this one here, and then I started seeing numerous other pieces that looked very similar to it in the CT data. So they seemed to be devoid of metal, and they had a similar sort of grayscale, similar sort of morphology. So I did a few other samples, and so these are the 3 biggest pieces that I've done. They were about 200 grams each, and then I've done some smaller fragments as well, and so far I found over 20 similar clasts to the pebble, which is quite exciting because then we're starting to say just how common this sort of material is in meteorites without ever cutting them up. Then we did cut them up, so you have to do some amount of destructive analysis. So here, for example, is where I've cut this one up. And we made these little polished blocks with a bit of the sample inside. So I chipped off some of the sample, which was sent for oxygen isotopes. I've kept another piece for iodine xenon dating, and then we put one piece in to do a sort of characterization via SEM. And so these are 4 of the casts that we've picked to focus on. And this is a false colour map. So the most important bit really to get from this is that you see what bulk Barwell looks like around here. So it has these chondrules in it, it's got fragments of metal and all sorts. These clasts don't have any metal in them, so that's good. That's supporting the idea that they've somehow lost their metal. We are very much in the process of discovering exactly what it means. We're doing some of these laser pits to look at trace elements and how that can tell us about how processed these different clasts are. And then this is, again, an oxygen isotope diagram. You don't need to worry too much other than to say this is where the H chondrites fall, this is where the L chondrites fall, and they're sort of, basically it's a fingerprint for which different parent body your sample comes from. Now the bulk Barwell falls here. These are Bob Hutch's bulk Barwell values, this is mine. His clast fell down here, which is why he was saying it was directly related to the H chondrite parent body, and my 4 clasts have fallen out here. So quite possibly there's more than one asteroid contributing to the clasts found within this apparently ordinary chondrite. So lots more to be done, hopefully exciting. Next example is Leoville, which I really like. It's a cool meteorite. It's a carbonaceous type meteorite, which means it contains some of the most pristine material that we have in our collections. And I was saying before, so this is a big slab that's about 3 centimetres across, which is great about this technique, is that you don't have to worry about destroying it, so they let you take big pieces out of the collection. And so I said before that these chondrules form in free space, so they tend to be spherical or have maybe an aspect ratio of between 1 and 1.2. Even just looking at this sample, I was like, what happened there? You know, what's the story? Because you look at these chondrules and they really are much more elliptical. And it's been described as one of the most severe deformation regimes in meteorites. And it's only ever been done in 2D. And all they really concluded was there was an anisotropic force causing these chondrules to deform. So we thought we'd stick it in the scanner. And this is the first analysis, so I started segmenting out, I think I did about 60 of them across the whole sample. So this is it, you know, from the front, from the side, and from the top, which basically shows you that from the top they're round, and from the sides they're elliptical, so they're basically pancakes in this rock. Fat pancakes, American pancakes. So I realised that there was no way that I would be able to scan able to segment every single one of these chondrules in the whole sample, and I didn't want to introduce any kind of sampling bias in it. So what we did instead was select 2 areas. So I'm not sure if you can see it here, it depends on the contrast, but there's kind of a meeting of 2 different lithologies within this sample. One on this side here, which appears to have much higher metal. There seems to be more matrix, more space in between the chondrules. The ones over here, which is doesn't have any metal, the chondrules are closer together, there's less matrix, and there are as well these fractures within there which have some weathering products inside. Again, we were just going for non-destructive analysis, so all we had was the CT data. So we cropped out these two different areas, and I segmented every single chondrule that was complete in those areas, and then tried to as well just categorise them by how much metal they had in them, because I noticed some of them had complete metal rims, some of them just had a blob on the side, some had no metal at all. And then what we can do is, within another program which is called Blob 3D, it's fantastic. I would say freeware is really important in new techniques like this, because the actual software is prohibitively expensive, and so it's labs all over the world that are creating their software to do this. And so these are the, in red is the chondrule that I segmented, and then it fits a perfect ellipse to it. And then what it can do is actually tell you the direction of the major and minor axes of that, which you can plot onto stereo nets or however you want to look at them. And it also measures the aspect ratio of them. So from the stereo nets we could see that all of the major and minor axes of these samples align. So there definitely is a foliation, and the foliation is defined by the direction of that minimum axis. So what we mean is the deformation happened when it was already in rock form, not while it was in space. And the aspect ratio, it's up to, I think, 2.1 was the highest that I measured. And what we see is that the aspect ratio actually decreases when the metal content of the chondrule increases. So it may be that they're adding some kind of strength to the chondrules, or meaning they deform less. And that also, in the lithology that had the lower matrix content, we see that the aspect ratio is much higher. Now this is probably because if you imagine you've got chondrules and matrix, where you have a lot of matrix and a shock wave coming through, the matrix will take a lot more of that compression before it starts to affect the chondrules, because it's more compressible, micro porosity within that matrix. So where you don't have as much matrix, the chondrules have to account for a lot more of that pressure before, without the matrix there. One of the cool things I've seen is that people take an unshocked piece, or a piece of a very similar meteorite called Allende, which is another carbonaceous type, and has spherical chondrules, and then they artificially shock it. So they'll put it in this thing called a light stage gas gun, where basically you have your meteorite here, and then you, at a known speed and thus shock pressure, fire something at it. And then you study the sample and see how deformed the chondrules are within there. So this is their diagram of artificially shocked ones. And when I put my data on the top, this is the range across here. So quite a big range in aspect ratios we see. And then this is the mean here. So we've got a range in shock pressures that could be as low as 10 in some areas, potentially that are shielded, but actually might be as high up as 30 gigapascals, which is pretty high for a shock event on an asteroid. So, I don't finish. Basically, there's a lot more that we can do with this without any elemental mineralogical information about it. We're sort of limited now. So we are going to have to face up to the potentially destructive technique of polishing it and being able to do some EDX, or potentially something called electron backscatter diffraction, which is actually where you can look at orientations of individual grains within that sample and see if it's deforming plastically or brittly. So that might be the next step if there's enough time, I hope. And then the final thing that I started looking at was a whole different way of investigating CT data. And so why did we choose porosity? It's really important to meteoriticists, and it's something that we don't really understand, because the porosity of meteorites doesn't match the porosity that we measure of asteroids. So there's something that we're missing here, probably that they may be these rubble pile things with lots of macro porosity that we don't pick up, or that doesn't survive re-entry. But it can tell you about the lithification history of a sample. So how did it go from all those dusty bits, rotating in a solar nebula, to stick together and lithify into what's a pretty solid rock now? It tells us about how shock will travel through a sample, similarly thermal diffusion, but also, importantly for certain groups, it tells you about permeability and thus the sort of potential for aqueous alteration on these bodies. So what we did is just sampled a load of ordinary chondrites. I tried to get them at different stages of metamorphism, different stages of shock. And this basically is a histogram. So this is all the light stuff. As you go on here, it gets heavier. And this is just the number of voxels of that grayscale in a sample. So you basically take a histogram and you say, right, here is where I determine the porosity is in a sample. So you're looking at the three orthogonal planes again, x, y, y, z, x, z. And we see that the really bright stuff is this iron nickel metal. You've got slightly brighter grey that is sulfides, and then all this mix of grey, which is the silicates. And then you see dark spaces in between them, right? Some of them even within chondrules. So we select that porosity. And we see Monod, which is a H4, so it's actually not very metamorphosed, but it's an S1, so it hasn't experienced a lot of shock, is what we call incompletely compacted. There's plenty of space in between there. It hasn't been sort of really heavily lithified, and actually when you pick it up, sometimes it falls apart in your hands, which is really annoying. Versus Kangastoonus, which is another very similar in terms of metamorphism, but when we look at the porosity here, we see it's pretty much constrained to where we have cracks, voids, veins in the sample. So I haven't seen any trends with the amount of porosity based on the metamorphic grade of the sample, so how much thermal metamorphism, how much heating it experienced. But definitely there is a trend with shock. As you increase the shock stage of the sample, the porosity decreases. It's quite there's probably a lot more to be said about the relationship between the two, because as you increase shock, you are decreasing the porosity. But then at a certain point, once you have a very lithified, non-porous sample, when you increase shock, you're actually creating veins and other shock features. I think I'm on time. Okay, good. So this is purely thresholding, so it's a different way of investigating CT data. Why I think it's important in porosity, because there are other ways of measuring porosity, okay? If you have a normal rock, you may want to dunk it in water and use Archimedes' principle of displacement. We don't want to put meteorites in water. So you may use helium pycnometry, which is based on the ideal gas source. You basically look at what volume of helium has been able to go into a sample, which is great, but it just gives you a number. You know, you may have two meteorites that are both 10% porosity. One is this really sort of incompletely compacted porosity all around all the grains, and another one just has a huge crack in it. And actually knowing where the location of that porosity is crucial to understand the origin of where it comes from and any trends there are. So I think the thing that CT can be useful for here, even though you're somewhat limited by resolution, is to visualize it as well as to quantify it. And maybe moving on from here, we'll also be looking at shape analyses, so similar to this ellipse fitting of the individual metal grains in the sample, to look at how aligned they are, and that will give us more information on asteroidal compaction, because that's related to shock. So yeah, I suppose my conclusions are that CT is really young, there's lots more to do, which makes it exciting but quite challenging. You really need to do it in conjunction with other techniques so you can provide a ground truth to what you're seeing. And also, there is a potential in so many different areas. I haven't even touched upon how we may be able to use it for sample return missions. They've done this for some of the Hayabusa grains brought back from an ordinary chondrite parent body. But I mean, if we are going to the moon, if we're going to Mars and bringing back samples, if we make those sample holders X-ray transparent, we'll be able to CT scan them and characterize that material before we ever open it up, expose it. We'll know exactly how much of the different types of material we have to be used for different techniques. So I think there's loads to do with it. And thank you to everyone who helped me on the way. Cheers. That's one of the particular results, actually.
Questions from Natasha?
Everyone wants to go to the pub, yeah?
Yeah. I've got to ask about people eating meteorites. What's that? What was found out?
I don't eat them. As a curator, I don't agree with eating them. Okay, so there was only one story about it, which is the Uralite meteorites. So, and I only know it anecdotally from the beginning of a book that a scientist had written on Uralites, but apparently when these things had fallen, it was near a village near the Nova Ure mountains, and I guess maybe they didn't know what it was, yeah, exactly, intrigued. And so the villagers all ate the pieces that they could find of that Uralite, after which all other Uralites are named. And then in the beginning of this book about Uralites, he said, yeah, lots of scientists who study Uralites actually wish that they'd eaten all of them because they're so complicated and difficult to understand. But yeah, no, I don't know. I guess if you love something that much, you want to eat it.
Since they have diamonds in them, they probably ruined their teeth.
That's true, or had very expensive, you know.
Any more questions? If not, I'd like to thank Natasha and Louise for a very exciting experience. Science Week continues with biology tomorrow and psychology on Thursday. The highlight tomorrow is the Rosalind Franklin lecture at 7 o'clock by Professor Elspeth Garland from the University of Oxford on crystallography from chocolate, food to drugs. And the Rosalind Franklin lecture is part of our theme response series introducing important women scientists in the area of Birkbeck has worked in, so there will be another sciences Rosalind Franklin lecture probably in 2 years' time, so I hope to see many of you there, if not tomorrow. So thank you very much for coming, and I do hope you enjoyed yourselves.
You haven't got your stick yet, have you?
No.
That's great, thanks.
Thanks.
Very dynamic.
Unless they fixed it.
Yeah, I know.
It's just
Are they not? Well done. Come to the bar.
Sorry? No, I left it on the side there.
Did we upload all of that from Panopto? Because I uploaded the first page. Yes.